Swayam Prabha. Digital India. Educated India.
The title of this presentation is Performance Driven Adaptive PID Controller Design, and I'm going to share with you the theory of this idea and actual experimental evaluation on the stir tank heater, for which I also have shared the case study with you. I want to acknowledge the work of Yoshi Onishi, who worked on this problem quite a few years ago, and it turns out this is very much what I would call a reinforcement learning algorithm. Adaptive control can be interpreted as a reinforcement learning algorithm. So the idea in this application is to do online identification and the design of an PID controller. Okay, so the outline of the talk is the motivation. Why should we be doing adaptive control or the performance adaptive control that we are working towards? Design of a self-tuning PID control system, look at controller performance assessment, followed by a simulation example, and finally an experimental conclusion. Okay. The features of the PID control method. PID stands for proportional integral derivative control. These control parameters are fairly easy to understand. The controller is also simple to implement on a real process, relatively simple to tune. However, it is not easy to design PID parameters for a time varying or an unknown system. You need to have an idea of the model for the process, and it is for this reason we can do online identification and subsequent control of such a process. Okay. So when you have a time varying or an unknown system, self-tuning control or adaptive control is truly effective for such systems. What do we mean by self-tuning algorithms? Here we have a conventional closed-loop system, and what we do using self-tuning control is collect input and output data. We feed that into a system identification block. We do online identification, as I explained in an earlier presentation on using the idea of recursive least squares. That's what we would be using in this box here. If you estimate the parameters, and those parameters are fed into the PID controller to compute the new control action. So this is what's typically done in a self-tuning or an adaptive control system. The method that we are proposing is retuning and identification should only be done when control performance is poor. One should not have to do continuous online identification. By continuous, I mean not at each and every sample. So in that respect, adaptive control, conventional adaptive control, can be considered to be an overkill. So here is the idea. Instead of doing identification at every sample time, measure the performance of your process. For that, you need to know the output Y You also need to know the target. The performance depends on how large or small the error is, and if it is decaying quickly or not. And obtain a measure of performance. We'll talk about one measure of performance that we have worked with. If the performance is good, if the performance is not good, turn on the system identification and feed those new parameters into the PID controller. On the other hand, if the performance is quite good, you need to turn identification off, and all you need to do is do conventional PID control on this system. Okay. So let's look at the following discrete time linear system. This is similar to the system, the ARCS process that we identified earlier. It is AY equals to BU and the delay for the input plus C divided by delta. So this term is slightly different than what we've considered earlier. In earlier examples, we only looked at white noise. This is known as integrated white noise. The term 1 over delta is an integrator. Delta, in fact, is 1 minus z minus 1. Okay. So here is the standard discrete time linear system. Many of the noise processes that we get are of integrated white noise type, and in any case this term delta can now be applied. We can multiply this whole equation by the term delta, and that brings us to the next set of equation. I just want to point this out. The PID calculations that we use for this controller based on what we call the GPC, General Predictive Control PID calculations, and the information is available in some of these papers. Okay. So the way we work is we would obtain a batch least square. I'll apply a batch least squares algorithm. Here is our sample time, Ts. So based on the current time t, we would obtain an estimate of the data with that we call theta hat of t. At the previous time interval, one would have obtained another estimate that we call theta at time t minus 1. And at the sample period even before that, this is the estimate that you would have obtained. So we have to decide what is the length or the width of the data that we want to use to obtain estimate. If the system is changing rapidly, then you have to make sure that the width that you use will capture the information in the data that you have. If the data hardly ever changes, then you could, if the parameters of the system hardly ever change, then you may even want a shorter data window. Okay? So given the length or the width of the data window, you compose the data vector z and y and calculate the system parameter theta hat. So here is the idea. We measured the output is noisy, so we need to filter it, and we filter it with a first order filter. The gain of the filter is 1, and you apply the same filter on the input as well. We compose the data matrix, and the data matrix now, because the equation is no longer A y equals to B u plus C. Remember, this was the ARC's equation with integrated white noise. If we multiply throughout by delta, we get A delta y equals to B delta u plus C. So our inputs and outputs are now delta u and delta y. And when you configure the data matrix, the previous data matrix that we had that I had outlined in the example for identification was simply yt plus 1, etc. Now it is delta y, delta u, and so on, and it is filtered. So we are feeding in the filtered value because we have a noisy process. Now, the other important thing to remember is this process, as in the STHI case study, was found to be second order. So we have two columns of the outputs. Column 1 consists of delta yft minus 1, and column 2 consisting of delta yft minus 2. And we also have several columns of the input. If we don't know the time, the number of sample time delays in the input, we have to have many more terms in the B polynomial in the discrete transfer function. So here we've configured the data matrix, and here is the output vector as well at the bottom, and we would apply this least squares solution to obtain estimates of theta hat, which consists of estimates of A1, A2, B0, B1 up to Bm. Many more B parameters than A parameters, because we need to capture the delay in the input. How do we assess the performance of the control loop? We measured the actual variance between the output and the target, and compute the minimum variance. So details of how to do that, this can be done in a data-driven system. It's not difficult to estimate the minimum possible variance, and the performance index then is the ratio of the minimum variance that can be achieved divided by the actual variance. So the performance index is obtained recursively, and we use that to design or to turn on our adaptive controller. So the performance index, we define the width of data window, we define the calculation interval. You want to compute the performance index over a short time period, and we compute the performance index nu of t, nu t plus 1, t plus 2i, etc., etc. And let's now apply this to a simulation example. We're dealing with a controlled system which has a continuous time transfer function such as the one shown here, and for t less than 7,000 the process is fixed. After the 8,000 sample interval, we change the delay substantially, and we also change the time constant. Okay, so we apply PID control to this system. The sampling interval is 10 seconds, appropriate because the time constant is 57. So the time constant is at least 1/5 of the time constant. The width of the window for performance index calculation is 300. We calculate the control parameters after every 10 sample intervals. Width of the window for batch least squares is also 300 samples. The filter parameter is 0.2 over 1 minus 0.8. The gain of this filter is 1. And the PID controller parameters are obtained using the GPC algorithm, where we have to specify the prediction horizon and the value of the lambda. So here is what happens. The process is such where the delay changes significantly at the 7,000 second interval, from roughly less than 10, 7 units of time, to almost 49 units of time. The fixed PI parameters for a fixed PID control system is shown here. These parameters are calculated from the initial value of the system parameters, and here is the result. The output is fairly steady up to the 800 sample interval. As soon as the delay changes significantly, the output becomes somewhat oscillatory, and the corresponding input is also quite oscillatory. The performance index falls as soon as the delay changes, and you notice that very clearly. The delay changes at the 800 sample instant. So performance degrades after the 800 step. Here is the performance index. The performance index for the first 800 samples is quite good. It's almost 0.95, very close to minimum variance control. But as soon as the delay changes, the performance drops significantly. So let's try and do so that was the fixed parameter controller. Let's try and apply system identification and adjust the controller parameters at every sample instant. If we do that, the result is, of course, better than having a fixed parameter PI controller. The variance, though, of the output is somewhat large, but nevertheless, control performance is not so bad. The performance drops after the 800 sample interval to roughly 0.8, but before that it was quite good. Okay, here are the parameters that are estimated online, the trajectories of the parameters, and what you notice is when the change happens, the parameters have a lot of variability. Here are the controller parameters Kc and tau I. Tau I corresponds to the integral time term. Kc is the proportional gain. And in continuous adaptive control, the gains do change quite often, in fact at every sample interval. If we do performance adaptive control, where our threshold for the performance index is 0.6, we would like to maintain a performance level of at least 0.6 relative to minimum variance. So if it is greater than 0.6, you don't need to do system identification. Sorry, you don't need to do system identification. You turn system ID off. If it is less than 0.06, meaning performance is indeed less, you have to turn on system identification and compute a new set of PID parameters. So here are the simulation results with that performance-driven adaptive control. This is where the delay changes, and it takes a little while for the controller to quickly estimate the new parameters for the controller, and it does try and bring the controller to good regulatory performance. The performance index does indeed go below 0.6, and thereafter it comes back. Okay. So if we do performance adaptive control, we will only do estimation when the performance drops below a threshold, and therefore the estimation is only done for the first 300 sample intervals, and then again at the 900 sample intervals up to 1100, when performance drops below a certain level, we do system identification, compute the parameters, and generate new PID constants. So here is that result. Kc and tau I do change after when the system identification is turned on, because the performance index goes below a user specified threshold. Important to notice that adjustment is only done at these small periods, so we're saving a lot of computational time. Let's do this now on a computer interface pilot scale process, where we are trying to regulate the temperature by manipulating the steam valve. And what happens here is we are feeding the output, the temperature output as measured at thermocouple 1 for the first 800 seconds, and after the 800 seconds period, we're switching to thermocouple 2. So as you would expect, there is going to be a significant delay in measuring the temperature at thermocouple number 2 because of the transportation time. This is a long pipe. Here is the stir tank heater. Here is that long pipe, and we are measuring the temperature here at thermocouple 2 and here again at thermocouple number 1. The sample interval for this is 10 seconds. The width of window for performance index is 300 samples, and here are the different results, and we have to filter the output with this filter. Okay. The fixed PI parameters, if you only do fixed PI control for this same process, including the time when we switch over from thermocouple 1 to 2, these are the parameters, and here is the result. So the result for the first 800 sample roughly is very good. As soon as you switch to second thermocouple, the system becomes oscillatory. Not only that, the output also chatters, and this is what you do not want to see happen, because it will wear the valve out, and this is not good for the process. So if you measure the performance index, it does go significantly below 0.1 for this case of fixed PI control. So PI parameters were tuned at every, so that was the case for the fixed PI control. Now we are going to tune the parameters at every sample, okay? And the result is quite good. If you do the adaptation at every sample, the output signal is very steady, and the input signal also is non-oscillatory. The performance index throughout the entire duration of this experiment is higher than 0.7, almost 0.8 or 0.89. So this is relative to minimum variance control. Remember that. So here are the trajectories of the estimated parameters. Remember, we are estimating the parameter at each and every sample period. In the beginning, we have to collect data for a certain period before turning the identification algorithm on. Once you turn it on, here are the results, and what you notice is the variance of the estimated parameters is quite high. You may not want something like this. Here are the changes in the controller gains and the integral time constant using the newly estimated parameters. Now let's apply performance adaptive control to the same system. Our threshold is that the performance index has to be greater than 0.6. If it is greater than 0.6, you don't need identification or adaptation. Turn everything off. Let the controller do the job. On the other hand, if it is less than 0.6, you have to turn the ID algorithm on, do online recursive least squares, feed in those parameters to come up with a new controller constant. Okay. So we apply the performance adaptive control algorithm to this process, and notice we get very good control, with the exception of a few sample intervals after the delay was changed in this process. Remember, we switched from thermocouple number 1 to thermocouple number 2. But other than that, we were able to obtain very good control. And the performance index also improves significantly. We are only computing the parameters, doing identification for too short duration. Here, when performance was below the threshold, and again at the second interval where performance drops below the threshold. So the estimation is only done for too short periods. Otherwise, the estimated parameters are more or less constant. We update the gains with the newly estimated parameters, and we see quite a bit of change in the proportional gain and also in the integral time constant. So adjusting is only done for these two periods shown by the red arrows. In other words, we are not adjusting the parameters at each and every sample interval. That's classical adaptive control. It is an overkill. We're only doing the adjustment for when the performance drops below the threshold. So to conclude, self-tuning or adaptive PID tuning has been constructed using batch least squares, and we've demonstrated this on the simulation example and also on an experimental process. Retuning and identification should only be carried out when controller performance degrades below a user specified limit. Control performance is calculated in an online manner over a user-specified time window with some overlap. And the identification is also done on a batch of data. It's almost like a moving window with overlap. So we're saving a lot of computation time, and this would be something that would be useful in any adaptive system. Remember, adjusting parameters at each and every sample interval is truly an overkill. So this is a more appealing, practical approach for adaptive control. Okay, just want to acknowledge the work of Benga Adelea, Ian Elaine, various CPC group members, and I know Yoshi Onishi wanted to acknowledge the support from the Ministry of Education in Japan. Also want to thank NSERC Matricon Suncor ICOR Industrial Research Chair Program for allowing us to do these experiments. Thank you.